Linear mixed models again, so just repeat what we've done. So because that is kind of a crucial point, because later today I'll start introducing Gaussian processes, which are basically linear mixed models or Bayesian linear regressions, just that you kind of completely get rid of these parameters in the linear regression, and because we have to get a head around this, I want this to be really all clear. So I mean, so we wanted to look at linear mixed models in the context of GWAS, as always, where we do genotype-phenotype mapping. So basically, we look for associations between SNPs and the phenotype, where the actual causal SNP is not measured, but instead we have some other linked SNPs, which causes associations. And well, if we don't have linked SNPs, then hopefully there's no association. That's the theory, but in practice, we typically work with natural populations. So there is stuff like population structure relatedness, which causes basically correlations across all the SNPs that we're in the genome, and for that reason we get spurious associations that we have to correct for by kind of taking this population structure into account. And well, the problem with this is we need efficient algorithms. We need models that can deal with complex diseases. Where actually, we don't have just a single causal variant in reality, but many of them. So we think about how we can find models to better model them, and how we can also. That's something that I didn't talk about last time, but that will come today. So once basically associations become too weak because either effect sizes are too small or the SNPs are too rare, what can we do? And we'll see that we can do all of these things with linear mixed models. Okay, so how do we do it in practice? Well, we write down this model for association between the SNP and the phenotype, which is, in the simplest case, a linear model. We basically have the SNP x times the weight beta. And in the simple linear model, we assume that the data is independent, right? So if you have a likelihood ratio test, we have the model with the SNP versus we compute the likelihood ratio between the model with the SNP and without. And if we now have population structure, then this independence assumptions comes back and bites us, because we can basically think of population structure causally as having clusters in the data. We have relatedness, and which is again small groups of individuals that are very similar in the data, and also on the phenotype. And because of that, if all the SNPs are correlated within families and the phenotypes are very similar within the family, then you have an association between the SNP and the phenotype, even though there's nothing systematic, nothing causal actually there. So, and you can think of this basically as a model misspecification. For example, if we have two individuals and we measure SNPs or phenotypes between them, they are actually correlated due to these different forms of relatedness, but the model, it doesn't assume so. So it will observe many correlations that it doesn't assume, and so it gets overly excited and spits out a lot of false positives. We say that, okay, we can kind of get estimates of this amount of inflation because we have so many p-values that we can draw these quantile plots where we draw the observed quantiles versus the expected quantiles under the null, and if we see a strong deviation from the diagonal, then This basically gives us as a measure of the mismatch of the observed distribution from the null distribution. Note that you actually assume, hopefully have some mismatch, right? Because you hopefully have some signal in the data. That's the goal of the whole thing. And with modern studies of hundreds of thousands of individuals, actually, you will get some of these lambdas that are larger than 1 just because you have so much signal. But you can kind of get an estimate how much the lambda should go away from 1. So that's just a little side note. So it's, if there's inflation in the data, it doesn't mean that there's population structure yet. But if there's an insane amount of inflation, then you have problems. And there's always this question whether you want more power or you want to be really conservative. And I think if you ask different people, they would give you different answers. If you ask orthodox statisticians, they would say, oh, always go conservative and don't have any false positives, basically. And, well, various ways to correct for such population structure, genomic control, linear mixed models, and talk about several things that we kind of found out about linear mixed models or about population structure correction using linear mixed models in our research. So this genomic control factor, again, the slide basically says that you can use this genomic control factor to correct just by taking all your test statistics and dividing by it. For that reason, well, because if it's larger than 1, you kind of say you have inflation, so you have too many significant results. But if you divide by all the test statistics by it, then of course you also divide the median by it, so it will by definition become 1. And you get rid of this. Problem is, it doesn't look at the data, and it's very conservative. And a more reasonable approach is the linear mixed model, which, as we said, basically it introduces a matrix K, which is called the kinship, or I mean, it's a covariance matrix, so I like to call it a kernel because I have a machine learning background, which basically typically is estimated from SNP data. And what it does is basically if 2 individuals are very similar, then they have a high value in that. And if they are dissimilar, then they have the low value in that. And it's a covariance matrix, so it basically if you have a high value, you have a large covariance. And it's estimated from SNP data, so it's basically a covariance in the genetics. And how is this used? It's basically used to sample from a Gaussian distribution, from a multivariate Gaussian distribution, a random effect, which we call the population structure now, which is just added to the mean of the regression model. So basically, your phenotype is now the SNP effect that you're testing plus a contribution by this global population structure. And well, I mean, this is a hidden variable. What if you're the way to treat hidden variables is basically to not look at a single value of it, but take its whole distribution into account, because we don't know the real value. So basically, you integrate it out over its distribution. And if you do that, you can do it analytically. It actually goes away from the mean of the distribution, but instead, this K matrix appears in the covariance of the model. So we now have a model that looks very similar to a linear regression model, just that instead of having independent covariances, independent variances, we have now a dependent covariance term. Well, empirically this works really well. The problem is now we have, I mean, the way it works is it actually accounts for these systematic covariances due to genetics. The problem is we have now replaced a very simple, also computationally very efficient model, namely the linear regression model, by one that is expensive to compute because it basically you have to do cubic operations in this K matrix. So estimation is now the problem. And we have to find, for example, some variance parameters that trade off the amount of population structure versus the amount of noise, random noise, independent noise in the model. And we have to estimate this from data. It's non-convex problem, so even if you have a solution, it's not easy to test whether it's the optimal solution. And, well, there are ways to get rid of this, and that's basically if you can replace a two-dimensional problem by a one-dimensional problem, it's much easier because we can just evaluate it on a line. We can just try out every point on the line, and then we get a curve, basically, that's the likelihood. If that's fairly smooth, then we can assume we have probably found the optimum. And the way to do it here is basically to replace these two parameters here by basically by introducing the ratio of the two variances. And if we introduce the ratio here, I mean, we can alternatively also do it the other way around, and it appears here. In which case this would be a sigma e, or it would be this sigma here. But you can see that this term is exactly the same as this, because we have sigma g times k and sigma g times this ratio, so sigma g cancels, which is just this. It's exactly the same thing. But the nice thing about this form is that for a given delta, all the other parameters follow in closed form, which basically means we can evaluate the maximum likelihood given delta, because we can basically take the model, maximize everything with respect to all the parameters but delta, because delta is, we just try out different values. For that reason, optimization becomes very easy, and yeah, we can even plug in some other optimizers that are even faster than going over the grid. The problem is still we have to try out, basically for every k plus delta I, we still have to invert this matrix, which is a cubic operation. But, well, we can, as I said, we can analytically get the maximum likelihood parameters for beta, which looks very similar to the maximum likelihood parameter of in a linear regression, just that instead of, I mean, basically wherever we have some inner products between the x's or between x and y, which in the linear regression case had a kind of, you can think of having an identity in here. We have now this k plus identity inverse. And also for sigma g, I mean, I won't go through them now, but this is also very similar to the variance estimate in a linear regression case, where instead of just having a sum of square, you basically, where in the sum of square you can also write as basically an identity inverse. You have now this squared form here, involving k. And yeah, a way to get around this problem, basically that you have to do these inversions for every value of delta, is using the spectral decomposition of k, where you have the eigenvectors, eigenvalues. So this is just replacing k by its spectral decomposition, so it's the same thing. And the nice thing about the spectral decomposition is that basically U is an orthogonal matrix. So if we multiply U by itself, then we get an identity. And we also know if we have a Gaussian distribution in Y, then we can basically, for every linear transformation of Y, we can also write down its distribution. So if we multiply Y by these eigenvectors, then basically we have to multiply the mean by the eigenvectors and the covariance term on both sides by the eigenvectors, which leaves it as a diagonal matrix in this case. And, well, just kind of hand-wavy, what are we doing here? We kind of look at the data in a different coordinate system, basically, where these dependencies due to genetics are actually independent. And for that reason, we can use computational methods that are marginally more complicated than a linear regression. This is FastLim. It's exact. Very good. And yeah, so this is now the introduction to the linear mixed model. We said that actually, if we look at the linear mixed model a little bit closer, what we actually do in the reality, we don't just use any k, but typically we use these covariance matrices that are basically just an inner product of a matrix of SNPs with itself. And if we do the math, then actually this follows as being equivalent to Bayesian linear regression, where we basically have, well, this is the SNP that we're testing, and we have now all the other SNPs, or all the SNPs genome-wide that we used, or all the SNPs that we used to compute this K matrix as a covariate in this linear regression, but we integrate over the weights. And to give this kind of an interpretation is that, well, we use all SNPs as regression variables because we want to take into account other causal effects, other confounding effects in the SNPs. But, well, I mean, we cannot actually write down the true set of SNPs, so we kind of give it a Bayesian treatment where we say, okay, because not all of these will actually be different from 0, we marginalize them out and say we place a prior over them and get rid of them this way. So this is kind of a Bayesian smoothing approach. And we only do maximum likelihood on this parameter here, and we treat these as in a Bayesian way. So that's also why it's called a mixed model, because some of the parameters are being integrated over. So some of them are random, and some are not integrated. So it's a mixture between a Bayesian and a frequentist approach, kind of. For everything that you're not interested in, because you don't want to answer any questions about this part. You only want to answer a question about this beta, well, because that's the parameter that you're testing. It's being treated Bayesian, and everything that you're interested in, you treat in a frequentist way. Yeah.
And so the X typically use all SNPs even while you're testing?
Well, in the traditional approach, yes, because in a traditional approach, you would use all the SNPs here to compute this matrix K, and that. But the question that you're answering is exactly what this proximal contamination problem goes to, because it shouldn't include the one that you're testing, because, well, if the same X also appears here, then it's already in your null model, because your null model is this, which already includes this. You don't maximize over it, you integrate over it, but you already take some signal from it into account. For that reason, you lose power. Exactly. Yeah. Okay, so let's translate this again to the graphical models world. So we have multiple SNPs that kind of regulate the phenotype. We have some that are linked, so where we see association. We get population structure, which makes all of these dependent. For that reason, we get spurious associations. We take the population structure into account in order to block basically the path between this one and the phenotype to get rid of the spurious associations. But the alternative, this is now the linear regression view, is basically, well, actually we take other SNPs into account by plugging them into a Bayesian regression as covariates. And these two views are equivalent. It's just writing the model in a different way, but the math is the same in the end. And now the question is, so basically in this view, the linear mixed model accounts for model misspecification because we use a very simplistic model which only involves this SNP and the phenotype, whereas the true underlying model actually also involves all the other causal variables. And so it's kind of a way to account for this misspecification by taking them into account. The problem with this is you don't know what these are. And that is why we have to integrate over the parameters of them. Even if we knew what they are, I probably would prefer integration. But that is only my view. Well, but this is now basically a research question that we asked ourselves a couple of years ago. Can we do better in using all SNPs for correction? And the one answer is that if we do various variable selection approach, we can often do better. Not always, but often we can. So that is if you have some reasonable way to narrow down the SNPs, then try not to use all. And the other thing is exactly this thing that, well, if we include the SNP that we're testing or ones that are in linkage to it into the model by using it to compute this matrix K, then we basically lose power because we reduce the association between this marker and the phenotype. Well, a way to correct for this is basically by removing those SNPs from the computational similarity matrix. And the problem is, if you do this completely naively, where naively basically means whenever we test, we exclude the windows and compute everything. This is not feasible, so we can either do something that is really simplistic, like do it in blocks, like a whole chromosome, remove the whole chromosome, and then have a different K for each chromosome, or you can use some low-rank tricks. And this is just this experiment that demonstrates the effect of this proximal contamination, basically by looking at kernels that include different distances. They all have the same number of SNPs, so they all should, in theory, have the same amount of correction potential. But going from 0 to 30 to 16, the distance between the SNPs tested and the SNPs in the kinship matrix increase, and for that reason, lambda also increases, which is, of course, not a difference in population structure. Just because you use a different set of kernels, of SNPs, there shouldn't be more or less population structure. It's just correlation between the SNPs that you test and the SNPs that you use to correct. And well, you can use low-rank updates because it's just a linear kernel. So basically, this kinship matrix is just a sum overall contribution of all the SNPs that are being computed. So we can just take the total one from all and then just subtract the ones that we want to get rid of. And because it's typically few, we can do that in less than cubic time. That's the idea. I won't show you the details here. Well, this is a table that demonstrates this effect, where we're basically just using all the SNPs versus all the SNPs but doing exclusion versus one that doesn't do exclusion. Basically, this translates into a difference in lambda, but also a huge difference in the number of significant SNPs, which is basically here, in this case, almost a factor of 2. Okay, so in this model, we said we have these two parameters here that now summarize basically all the values of the betas here. So instead of having one parameter per SNP, we only have one parameter that just shows basically reflects the overall amount of variance due to those SNPs, which makes it much easier to do inference. Because with more parameters, you get a more complex model, increases variance in your estimates. That's something that we saw in the linear regression example. And well, in theory, you can also use in the same way as you use the axis, we can also use basis functions. For example, if you're interested in interactions between the SNPs, we could use a polynomial, and then you just get a different k by plugging in these polynomials here, polynomial basis functions. So this is quite nice. So we can basically play around with this k, and then this means we're looking at different things in this model. In GWAS, we talked about heritability, and that there's this thing of missing heritability. And well, if you do the GWAS, if you test, then the amount of heritability that we actually can explain with the SNPs that are significant is very low. And in order to see how much variance can we actually, for a hopefully infinite sample size with a set of SNPs that we have, we can use linear mixed models to get an estimate of this. And this is something that Peter Vischer and colleagues have done like up and down, where basically they use this idea that, okay, well, I mean, basically we need the variance contributions of all these individual SNPs, but that are causal. Now we implement, basically we don't know what the causal ones are, so basically we use all the SNPs that we have, and then basically we get the amount of, this model will explain the amount of variance tagged by these SNPs that we have. And well, we want to get rid of the parameters, so we integrate them out, and now we write the whole thing in the same sort of kinship matrix, just that we now divide by the number of SNPs, such that we can basically get a matrix that doesn't depend. Right? Basically, if you use more SNPs to compute this matrix, it will still have very similar values overall. So the amount, this parameter sigma squared g here will tell us something about the variance explained by all these SNPs. And the sigma squared identity, so the sigma squared e here, tells us what is not explained by SNPs. What do we have to explain by environment? And so basically, by looking at these two parameters, we can tease apart the variance due to genetics and the variance due to environment in the phenotype. And well, if you maximize these with respect to parameters, we can now get an estimate of the amount of heritability, which is defined as the variance due to genetics over the total variance of the phenotype, and the total variance is just the sum of the two. And well, we can do that for different types of basically, if you plug in different SNPs, we get basically different h-square values. Basically, whatever we don't include in this matrix here, we have to pull in here. So we can, for example, plug in individual chromosomes, and then everything what is not on that chromosome would have to be explained by this other sigma squared here. So we can estimate heritability genome-wide, heritability across chromosomes, and so on and so forth. I think we already saw this slide here. Am I going back? Maybe I included something twice. Okay. That was basically recapitulation of last Monday. This Monday. And the one thing that I didn't talk about, it's basically very similar again in application, is, well, we said we can estimate those variances and we can estimate heritability, but we can use the same trick also for testing. And now say we want to, well, we have a given set of SNP that we are interested in. We want to test whether they actually jointly explain some variance in the phenotype. For example, if, say, each of those is a rare variant, and basically for rare variants, it's very hard to get significant tests in a regular manner. We can say, okay, let's look at all the variants in a region and say, is there something in this region that is significant? And well, in order to test that, we have to ask the question, is the sum of all these effects equal to 0 or not? The null model would be a 0. This is the mean of the phenotype. The problem with this is, if these are many, then we basically get huge. We can do that. We can do that in standard linear regression, where we now basically test the sum of the beta weights or something like that, which will work in the same way, because we can again use these Gaussian formulas to derive the distribution of that. The problem what we observed is if we have many of these terms here, that corresponds to the setting where we had many basis functions. In the one example, we just get these. Even if there's nothing, we will get these extreme parameter values. So there's just by increasing the number of terms, you increase the amount of randomness in this, and so it will be very hard to show significance if we use this approach. But we can use the same trick, and that is basically by integrating out these betas here. We will get again a variance component model where now the equivalent question is, okay, if we have this k computed from those SNPs here, is the variance of this k significantly larger than 0? So is the amount of variance explained by this set of variables 0 or not? Where unequals to 0 is now larger because these variance parameters are all larger or equal to 0. So there are no negative values here. And that is successfully done. Many people do that. You can write down tests. They're actually quite complicated. But so I won't talk much about the technicalities of these tests, but just I just want to introduce it as an application of the mixed model here. The problem here is now that if you have population structure when testing a single variant, you will also have population structure if you test multiple variants, and it will hit you even harder. Because say each of those is affected a little bit by population structure, and now you're basically summing up over little contributions of population structure, and you will have a large contribution of population structure. So just by increasing the number of variants here, you increase basically the number of false positives that you get due to population structure. So what you want is you want to still have some sort of population structure in here. And the way to do this is now by including a second kinship matrix, which is actually now represents the population structure into the model. So you have basically here the set of SNPs that you're testing, and here, for example, all the other SNPs. Right? Say this is all the SNPs on one chromosome, or all the SNPs in one genomic region, the region of all this of one gene, then this would be everything except that. I mean, we again have the same problem that we don't want to include the ones that we're actually testing here, which is due to proximal contamination. Will they have the same effect? Is this idea clear? So now, yeah?
You're taking these SNPs that you're testing from wherever you want.
Well, I mean, you basically have a set that you want to test, which could be, for example, everything in a region. Or what people also have done is they, for example, say, well, we have a bunch of candidate genes, and then you basically take which are in a common pathway or so. So basically, all the SNPs in the genes that belong to those pathways are included. If you want to test rare variants, then, for example, it might be all rare variants in a small region, something like that. So this is now, I mean, you can think of many things. So this is just the test. What you put in there is whatever you want. All right. So it's important to correct for population structure, which these methods don't do here. But then we can use a likelihood ratio test. And well, the test that typically people use is a so-called score test. I want to talk about the score test right now. It's basically just think of it as writing down the likelihood ratio and doing a very simple Taylor expansion to it, and then you have something that looks like, I mean, basically you do a second order Taylor expansion, so you have a quadratic approximation to your problem. And usually things that are quadratic, you can think of something that is Gaussian, that looks like a Gaussian, because you again have a sum of squares in the Gaussian. So using this approximation, you can write down an approximate test, which is computationally pretty simple. In the general case, testing fixed effects is easy, but getting the null distribution for these variance components models, where you basically now want to infer whether this parameter is significantly different from 0 or not, is not that easy. So writing down this distribution analytically is basically impossible. And one problem for that is that if you fit these models analytically, a lot of the times this parameter will actually be 0. So if you think of a distribution where, say in 50% of the cases, a parameter is 0, and in the other 50% of the cases it goes a little bit away from 0, so there are actually no, I don't see any chalk. Right where?
Oh, right in that hole.
Oh.
Yeah.
So yeah, I have to. Okay,
Oh, there's also, is there some up there?
Oh yeah. Okay, so now say you basically get different data sets and you fit this problem, and well, most of the time it's 0, so you basically have, if you look at the histogram, you basically have a big spike at 0, and then you have something that, I don't know, has whatever distribution, say it looks like a half Gaussian, but you already know that it will be very hard to find one analytic distribution that explains this. I mean, that looks like a spike plus something else. I mean, it's very hard to approximate, for example, by a Gaussian, right? Because a Gaussian would look like that. So that's just some hand-wavy explanation why it will be hard to write down the distribution of this. But what you can do is, of course, you can do permutations. The problem is that, well, in order to do these permutations, now you have many cubic problems, so it's really expensive. But what we did, and that works really well, so this is now again what I drew. This is basically the number of zeros, and you have this long tail of non-zeros. So it's even more extreme than the way I drew it. You can do a little hack, and that is basically, well, in order to get significance with permutations, you basically say you do 10,000 tests and you do one Ferroni correction. You want actually p-values that are pretty small, right? So you need to do a lot of permutations to get actually resolution in that range where you can actually get significant p-values. That is very hard to do, but what we did is say, okay, we do only very few permutation, well, very few, still, I mean, as many as we can get, and then we basically fit just some parametric distribution to these null to the null distribution that we found. So basically, we get some coarse distribution, which, if we had infinite amount of data, we can basically get the full tail, because we're interested in this tail, right? Because these are larger sigma square values, and we're interested in this tail, and this is where we want to test. The problem is that if we do very few permutation, we probably have one observation here, and well, the further we get to this part, the more observations we have. But we're not really interested in this part. But what you can do is basically you can take your few distributions once you have enough that you can reliably fit a simple function to this, and then you can use the simple function instead. in order to extrapolate in the tail. So it's basically a regression problem then. And well, empirically this works really well and gets more power than the score test. Just showing some plots of power. It's again taken from a scientific talk, so it's not that important now. Okay, so this is the part about linear mixed model applications in genetics that are simple and straightforward that I wanted to talk about, and those are probably the most standard and most important ones that you will see in genetics. So it's basically testing of single variants, testing of multiple variants, which is equivalent basically to saying we estimate heritability. Is this heritability due to this set significantly different from 0? So it's basically just, the set test is basically just putting a significance test on top of this heritability estimation. And was that it? I think that was all the ones that we took. Okay. Yeah. And well, mixed models, the problem with this is you basically replace something that is very easy to compute, but does poor modeling against something that is much harder to compute, but allows you to more robustly model your data. And this creates new problems, and that's why computer scientists can help a lot here and improve the computation. Are there questions to this part? Let's do a short pause before we start with the Gaussian processes. Yeah, and yeah, so in the next half hour you will completely understand them. Okay, so I'll try to use as much intuition as possible. And what comes now? Okay, so why do we want Gaussian processes? We say, yeah, we have linear models with basis functions. Where basically the basis functions, they will basically result, the choice of the basis functions will result in how our model will look like. If we use polynomial basis functions, then we will basically fit polynomials. If we use something else, you fit something else. It's basically, you get the idea. And now the question is, well, if we increase the number of basis functions, our model becomes more complex. We have to regularize again. So what's a good number of basis functions? Or what kind of basis functions do we want? Right? So all of these questions are not easy to answer. Well, the Gaussian process is basically a way to do something like that without specifying how many basis functions you want. The Gaussian process will allow you to specify kind of a prior over functions where you can basically sample functions from, and you only specify this in the prior. You basically encode in, okay, will my functions be smooth? Will they be edgy? Or something like that, if you sample from them. What do you mean? And in Gaussian process regression, we will use these functions now as regressors, just like we have a likelihood, and the mean of our likelihood has a function in them, and we'll use a Gaussian process for this function. And then we have noise. But basically what a Gaussian process will do is basically once we specify them, we will be able to kind of fit distributions over functions where we have kind of mean functions and some error bars around them. And yeah, and the error bars basically will be small, where we have a lot of observed data, because there we will know the function very well. And they will be very wide, where we don't have enough data, because if we want to predict for a given x something here, that will be a very hard task, because we don't know how the function, they could go up, it could go down, it could, we don't know, right? So that is kind of what we want to do with the Gaussian process. But we can still do predictions. We can still say, okay, so I predict, for example, the mean of the Gaussian process here, but well, take it with a grain of salt, because my error bars are very high here, so I have a lot of uncertainty there. While if I want to predict something here, my prediction will be probably pretty accurate. Okay, so well, let's go back to the linear model first. In a linear model, we know how to predict, right? Basically, we estimate those betas, and then we use them. If we have a new x for which we want to predict the y, we use that beta in combination with the new x. So we have a training data set, then we have a new x star for which we basically compute the mean of y given that x star. And then the variance of y would be just the variance of that. That is the frequentist way of doing it. If we do it Bayesian, then we can also marginalize out those weights, where we said, okay, if you on the training data set marginalize over those weights in the linear regression model, we get this K matrix here. Right? So now we're basically back to the last talk, where we have some parameters in front of this K matrix, but we can use this K to do predictions. So it's just the question is, how do we do that? And that's something that I already tried to convey on the board and failed miserably. But let's try it again with slides. If you want to read further, there's a book by Rasmussen and Williams. I don't recommend it as an introduction, because it's more like a bunch of, so if you really want to get into Gaussian processes and want a lot of tricks, how to implement them, how to use them, then this is a good book. It's basically, that's what it is. It's a bunch of tricks. It's not a good introduction. The other books, like the Bishop book, are better, and then there are some other online tutorials. Okay. Okay, so how do we do predictions? Come to that in a bit. But one central thing about Gaussian processes is you basically have a Gaussian distribution with this matrix K as a covariance matrix. And this covariance matrix is now absolute central. People also call it kernel. We'll come to, why in a bit, because kernels are used in support vector machines, but those are the same types of kernels. Basically, the kernels in a support vector machine, if you plug them in a Gaussian distribution, there would be a covariance matrix. But Gaussians are nice. So, for example, if you have a two-dimensional Gaussian with some matrix K, which is a covariance matrix, we can basically write down the joint distribution, or the joint distribution over y1 and y2 kind of looks like an ellipse. And if we now sample from that, our samples might, for example, look like this, where we have many samples here in this dark area, and the samples are kind of spread out along those major axes of this Gaussian distribution. Well, you can do that for different forms of covariances. So you can have very low covariance, and samples will be basically pretty much spread out. We can have a higher covariance. If we have a high covariance, it means that it's kind of a little bit squashed. Or we can even have negative covariance, which means that if y1 is if y1 is large, then for example y2 typically is small, small, and so on and so forth. So basically, by varying the covariance matrix, we can get very different values for y1 and y2. How do we do inference? Say we know a value y1 here. What can we say about the value y2? The way to do that is conditioning, right? So basically, we just cut through here, and then we can get a one-dimensional Gaussian distribution of y2 given y1. So starting from the joint distribution, y1 and y2, which is the Gaussian distribution, we can get the conditional distribution from the joint over the marginal. And because we want the distribution of y2 and the distribution is Gaussian, we only need to look at the part that contains y2. This one doesn't contain y2, so we can ignore the marginal distribution of y1. And then use completing the squares in order to get the distribution of y2 given y1. And the interesting thing is that here, in this Gaussian distribution, we assume that the mean is 0. But this was also a zero mean Gaussian distribution. And as you saw, the conditional mean of this was not 0. Right? So by doing this conditional operation, the mean changes. And if it's initially 0, it will become non-zero. And just for simplicity, we'll only care about zero mean Gaussians in the following, because it just takes away a lot of writing. You can add in the means if you want. So by completing the squares, we'll get a new Gaussian distribution in y2, which will have a mean that depends on y1. And, well, this is just doing it. I probably should have had some stops in the slide. Okay, so this is just what we had before. This is the joint distribution, right? So this is this part, which is the Gaussian in y1 and y2. So we have a squared form, y1, y2, times k inverse, times y1, y2. Now if we multiply these things out, no, these are just two one-dimensional variables. So these are just scalars, y1 and y2. It's just to make it really simple. We get something that is squared in y1, we get something that is squared in y2, and then we get the cross term, right? y1, y2. And then the next step is we reorder them. And actually what we're interested in, we want to get a distribution in y2. So all the terms that don't contain y2, we can completely ignore, and we just call them a constant, which in this case is this part here. It doesn't contain y2, so we can throw it out. In the end, we'll normalize, because we know it's a Gaussian distribution. So we're just left with these two terms. And now we do the completing the squares operation, where we need a covariance matrix and something else. And the covariance matrix we can basically get by looking at the squared term. And basically everything that is multiplied by the squared term, so if we write it in vector, it would be y2 transpose times k inverse times y2. Yeah?
The subscript for the k that was like that entry, right?
Well, it's basically k inverse. So basically k inverse. Well, k inverse 1, 1, whatever that means. It's basically just I write on k inverse as that, and I call those k inverse to 2, and then where those, I mean, those are not inverses to the to those parts of the matrices. It's just taking the inverse, and then so think of it like that. And you take the inverse, and then you do a subscript. Okay. Parts become constant. We can read off the covariance of a new Gaussian, or because it's a scalar here, it's only a variant. So we're getting Gaussian distribution over y2, and this is the variance. We can already read it off. And then we have this squared term, and then what we'll have is the term that involves the mean of this new Gaussian distribution. So in order to get the mean, we basically have to we can basically take this term here. Oh, what is happening here? I'm too close. I don't see the slide anymore in full. There's this term here. How do we get from here to here? 1, 2. It's been a while. You have to complete the square. So this, I mean, this is basically just plugging in the binomial formula. So we need something that is k inverse. Right. I mean, something is missing to get the square. So because in the binomial formula we have the cross term and then the new term. So we have to add that, and then we can read off the mean here, or the negative mean. Where again, everything that doesn't depend on y2, this here, we can pull into the constant. So we have now a new distribution with a mean that is non-zero, right? Something that depends on y1 and the variance. And well, that was not just a random two-dimensional Gaussian, but we actually want to use this for regression. So how can we use this for regression? Well, in regression, we usually have an x, and then we want to compute the distribution on the y. But basically, two x's, we can basically say we compute a covariance, basically like this x transpose, that depends on the x. And then we have a joint distribution over these, and once we have, from the joint, we can read off the conditional distribution. So observing this x1, if x2 is this, basically the conditional distribution is a Gaussian. Right? And now we can also extend this to a third point. So say we have observed these 2 points, we can basically now compute the conditional distribution of this given these other 2 points in a similar manner. And the only difference is here, yeah?
You're already assuming you have your k matrix, right?
Yes, that's the problem. Now that's basically the deal is the k matrix has been computed based on the x's. And which is in the case where we have 3 points, it would be a 3 by 3 matrix, right? And just can do the same types of computations. They get a little bit more complicated if it's a 3 by 3 matrix, but we can compute the conditional distribution of this y here given the other y's. The problem is, how do we get a covariance matrix like that? Well, if you have our x transpose, that is one way to get it. I mean, for example, we can also, but kind of, I mean, what they kind of should tell us is, well, if 2 points are similar in x, then they should usually be more covariant. There should be a higher covariance than if they are far away in x. Basically, it's covariance on y should depend on how close the points are in x. That's usually the assumption. For example, we could say, oh yeah, Well, for two neighboring x, you have a covariance of 0.6, and once you're 2 hops away, it's 0. That would be a very simple covariance matrix. Right? But that would be a way to do it. It would give you a Gaussian distribution. Which basically means that every point only depends on the point next to it, but to no other point. The problem is now that the ordering on y1, y2, and y3 matters, but that ordering could, for example, be given by the ordering of x. And the other way when we thing that we have to always take into account when we construct these covariance matrices is they have to be positive definite because they have to be valid covariances, right? And well, if we do inference in Gaussians, we always have to do inversions and all these things, so they have to be positive definite. Of course, we cannot construct covariances like this. We cannot just like, oh yeah, they look similar, so let's write down a covariance matrix that kind of says, so if something is close to each other, we give it a high covariance value. So we need kind of a general recipe to compute these covariances. And that is kind of the idea here is that in a Gaussian process, we basically have a covariance function, which basically given two x's, we plug them into this function, and this will give us a covariance matrix. This function typically have some parameters. So, and then for a given set of parameters, we will get a valid covariance functions for each pair xi and xj. And then basically by evaluating this covariance function for each pair xi and xj, we will fill the matrix K. For example, that's the most simple example is a linear kernel, linear covariance function, which is just what we used in the linear mixed model. So it's basically just taking the vector xi, for example, all the vector of all the SNPs, multiplying it by all the SNPs of the other sample, and that gives us the covariance between those. And then the parameters here, for example, would be some scaling, like the sigma squared g that we had. Right? So it's basically just what's the overall variance due to this thing. And it turns out if we use this sort of covariance function, then for every I and every j, we'll get every combination we get a positive definite matrix. And the types of functions that we get are linear functions. Right? Because we started out with a linear model and we got this sort of covariance function or this kernel when we did integration. A different, more complicated function is, for example, a squared exponential kernel, where, again, as you said, basically, if two x's are similar, they should basically have a high covariance. And in the squared exponential, the way this is being done is basically you measure the distance between the x's. So instead of taking the product, as in a linear kernel, you measure the distance, square the distance, so you have a squared distance, divided by some parameter, and well, take the negative of it. Take that into an x. So if the distance is very large, this will be small. So if the distance is very large, we will have very small covariance. And well, in this case, we have the two parameters here, a and l, where a is again just an amplitude of the whole kernel, and l is something that we call the length scale. Yeah?
What exactly is a hyperparameter?
A hyperparameter, so in Bayesian inference, you basically have parameters and hyperparameters. Hyperparameters would be, so parameters would be the model parameters that you place a prior over and you integrate them out. Hyperparameters would be the parameters of the prior that you don't integrate out. Those you specify in the beginning based on your prior belief. Basically, the hyperparameters are those that you have to specify in order to get a prior. And in here, the goal is to place a prior on the types of functions that we want to use in the regression. So, and the central point in the types of functions is basically this covariance function here. So basically, this covariance function is part of a prior. And all the parameters in this covariance function are hyperparameters. Well, and basically, this a square is just the overall amplitude. And then we have this scaling parameter, which in this case, we will see that this will control the smoothness of those functions. But again, you can prove that for every pair of x's that you put in there, and if you fill the matrix like that, you will get a positive definite matrix. And you can actually also show that this is kind of the limit that you get. We had the squared exponential basis functions before. This is the limit. If you set the number of squared exponential basis functions to be infinite, you will actually get something that looks like this kernel if you integrate out the regression rates. But this is just a side note. And, well, the covariance matrix, so basically you get by evaluating this function for every pairs of x's. So it's basically a kernel matrix that depends on all the x's and on the hyperparameters. So, well, how can we use this? For example, you have 10 points, right? You have 10 x's. x1, x2, x3, and so on, 10 of those. And, well, what this basically means is that if we evaluate for those 10 x's, right, -5, -3, -4, and so on and so forth, this covariance function, we get a joint distribution over the y values. And this joint distribution basically comes from sampling from a Gaussian. So if you take samples from a Gaussian with such a covariance function, we would, for example, get these green dots here. And what we just do is we just connect close by green dots. That's all that we do. So the covariance between this point and this point is given by the squared exponential with these two parameters of -5 and 4, and so on and so forth. So, and that basically means that you have a covariance between this point and this point just by plugging in the two x values and so on and so forth. But the funny thing is that these covariances are now covariance on the y value. So basically, if we now sample from so if you write down this 10 by 10 covariance matrix by evaluating all pairs of these x values of the squared exponential with the A3 and L1, then we get a joint Gaussian distribution that looks like that. And we now just plot basically x versus y. That's all we do. And one observation that we see here is that basically if we increase this parameter a here, the overall variance goes up. So basically you observe, I mean, it's just it's a scaling parameter, so it's basically you increase the variance in the y values that you get. So you get larger values, smaller values. Well, 0 is the mean. So we have 0 mean y values. So on average, all the y's are 0, but if we increase the a value, we get larger deviations from this mean. Now this length scale here, so we said is kind of a smoothness of the function. So for example, if we compare the red and the green, where the red has a smaller length scale, we don't see very much here, but we kind of see that the red one probably is a little bit more wiggly than the blue one. Those are not 10-dimensional Gaussians. How do we get, I mean, we can do the same thing for higher dimensions. Now let's just do the same thing with the 500-dimensional Gaussian, where, what are the dimensions here of the Gaussian? The dimensions are now values, basically I just walk along the grid, note the x value, plug the x value into this squared exponential kernel function. And then I get covariance functions, and then I sample from this 500-dimensional Gaussian, and now I just plot x versus y, and I get these smooth curves. And now you see basically that if you increase the A, you get, again, values that go further away from 0, and that basically that these red lines have more more changes in direction. It's like kind of intuitive. Not very? Okay. let's move on. I mean, I'll have some couple of more examples.
Can you explain a little bit more about what these plots, what exactly are you plotting a little bit?
Those are just samples from the prior. So you just say, I take all the x's on the line. Basically, I evaluate 500. Here I basically evaluate 10 points on x, and I computed the squared exponential kernel, which gives me a 10-dimensional Gaussian on y. It's a Gaussian distribution on y. Then I sample from this Gaussian distribution on y, just to get a random Gaussian sample, which is a 10-dimensional sample. And now I plot the x value that I use to compute the kernel versus the y value. And the covariance depends on, and we see basically because the covariance between the y values depend on x, that neighboring y values, neighboring x values yield similar y values. That's just the observation. And this is now just increasing the resolution. So instead of doing this on 10 points on this line, we just do it on 500 points on this line that are equally spaced. There are no observations, there's no data use, it's just using the x values, computing this kernel function, and then getting a sample from them. And the one observation is that basically the way we parameterize the exponentials now changed the way those functions look. Well, these are just, I mean, those were one sample of a 5. This is one sample, the dimensional Gaussian distribution. So in the 2-dimensional case, this was one sample here, right? Just that it's not a 2-dimensional Gaussian, but a 500-dimensional Gaussian. So each of the function lines is a single point on this plot for 2 dimensions. Look at the time. We have the time. 3:40. Well, how do we sample? That's probably. Let me look at after this. So how do we sample? Basically, well, we choose some discretization of the axis, which in this case was linearly spaced, you said, right? And we compute this squared exponential kernel for between all the pairs. In the one case it was 10 pairs, in the other one case it was 500 pairs. Then in math, basically we draw from this Gaussian distribution. It's a zero mean Gaussian distribution with this plugging in this k, and that gives us the values of y. And then we plotted x versus y, where x was used to compute k, and y were the samples from this distribution defined by x. Well, in kind of how do we program this? This is just using this trick that we can use random normal distribution, just a standard normal distribution, and then we can basically compute the square root of k, and then multiply, for example, the Cholesky factor of k as a square root of k, and then we just take these standard normal samples and multiply them. It's just this is just getting a sample from a multivariate Gaussian. So this is just this is something that we, because if we know the distribution of this, if we wanted to get the samples from a distribution of this, we have to apply a linear transformation to y, and the linear transformation is the square root of k. Right? So this is the way these lines were drawn. That's so far all the trick. Yeah?
The Cholesky factor is the square root?
It's one form of the square root. Yeah, that's one. So basically, compute the Cholesky of k, multiply Cholesky of k by y. Huh? The Cholesky factorization, that's basically, it's 1 square root of k, which is I think it's a lower triangle, depending on how you define it. Basically, k equals r transpose, where r is now the Cholesky factor of k. And R, for example, would be a lower triangular matrix. So it's 0. And you can do that for any positive definite matrix. Okay, we know it's by construction. We said we chose a function that gives us, if we evaluate it, a positive definite matrix, so we can do that. Well, why does this work? And the funny thing is that basically 10D and 500D Gaussian, we can go from one to the other very easily. For example, we can basically get from a 500 Gaussian to a 10-dimensional Gaussian either by conditioning or by marginalization. Or we can get from a 10D to a 500D Gaussian just by adding new points to the covariance matrix and sampling, conditioned on the already observed points. So, for example, we have 3, for which we have this covariance matrix, which we got from sampling by evaluating the squared exponential, for example, it yields these values, which defines a distribution, a joint distribution of y1 to y3. And now we basically we are only interested in y1 and y2. How do we do that? Well, we haven't observed y3. We only have its distribution. So the way to get there is by integrating over y3. So we take this joint distribution, which in this case might be the 500D Gaussian, and we want to go to the 10D Gaussian. The way to get there is basically by integrating over all the points in this 500-dimensional Gaussian that we didn't observe, that we're not interested in. And, well, how do we get there? So how can we get from this K3, which has this inverse, to K2? Is it this matrix or this one? Do we know something about the inverse? Is it this, the inverse of this? Or how do we get to the two-dimensional covariance matrix? A or B, which one is true? So if we start out by the 500-dimensional Gaussian. If we now only are interested in the covariance matrix of the 10-dimensional Gaussian, can we read it off the 500D Gaussian? That's the question.
Do you mean for A, do you mean K2 inverse? Or?
Yes. Huh?
Do you mean K2 inverse for A? No.
No, that's K2.
Oh.
Yeah. And it should be 0.5.
Okay.
By the way. Is that 0.5? Yeah. He's got lost. A or B? A. Yeah. I mean, yeah, it's 0.5. So basically, the way to marginalize is basically you only need the submatrix corresponding to the corresponding variables that you're interested in. So, and for a Gaussian process, basically the idea is that the actual Gaussian that you start with, the prior, is an infinite dimensional Gaussian. This is now a little bit philosophical because you're always interested in finite number of dimensions because what we have is a finite number of data points. So, and each data point is one dimension of this Gaussian. But in theory, we can basically place, basically x can be, if x is on a continuous scale, right? We can have infinite number of those, which would be an infinite by infinite covariance matrix. And now we can get to every subset by marginalization, which basically means from this infinite matrix, we only need the values that we actually are interested in. We only need the x's that we actually want to evaluate y for. So the way we did it empirically here was, numerically here, is that we basically just linearly spaced some x's here, which gave us a 10 or a 100-dimensional Gaussian from something that actually, I mean, the function in principle is infinite dimensional, right? I mean, every point in the function is one dimension, and they can be infinitely close together. And but for example, if you have training data points, we only observe, say, 100 of those. So we only needed a 100-dimensional distribution. So from the infinite dimensional distribution, we can go to the finite dimensional distribution only by evaluating the covariance function of these 100 points, not of the infinite many points. That is, now you know what a Gaussian process is. Thank you. Well, basically, the consistency rule is basically that. Okay, now I have to explain consistency. Consistency means that you can, if the, say there is some true function, you want to learn that true function, that with given an infinite amount of data, you will find the true function. That's what consistency means. And why is this the case here? Basically, if you had infinite amount of data, you basically would observe everything everywhere, and you would always, you basically get, you can go, I mean, you can basically take the infinite limit, and everything will be there. And for every finite subset, you can also write down the distribution. Yeah. Next time, we'll reiterate that, and we'll talk about a different view of Gaussian processes. Who's dead?
President's Day.